0, and 1. We're not going to get into what happens when b is equal to negative. That's more of an algebra 2 concept. But if you have any sort of fraction or decimal inside this parentheses, then you are going to start seeing decreasing outputs. Okay? Let's talk about what that looks like in graphical formats. Okay, so I'm going to give very, very basic sketches of graphs, but feel free to plug either one of these into y equals and pull up the graph to see for yourself what it looks like. All right, but 99% of the time, our exponential functions are going to have what's called an asymptote. It's going to have a bottom line that might be down here, it might be up here, it might be on the x-axis, but it's a line that your graph gets super duper 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 close to, but it never actually touches. So what happens on a graph is, for exponential growth, we start with a very, very, very small value back here, and it's so small that it almost looks like it's actually on the x-axis. And your graph, your calculator might look like it actually just stops drawing, but that's because the ink gets so close to the x value on the computer that it doesn't know how to communicate how close it really is. All right, so it's going to start off really super small. It's going to start to pick up and separate itself from the x-axis, and then it's going to hit your y-axis at your y-intercept. And this should match up with whatever your a value is. And then as we start to get bigger and bigger x values, this graph starts to pick up its pace and starts to increase faster and faster until it almost looks like an actual vertical line. Okay, that's exponential growth. Exponential decay is going to actually start at its highest point, or start at the biggest y value back here on the back side, and it's going to decrease super rapidly. So it came from somewhere up here, it's going to come diving down really super quick. It's going to hit that y-axis again at the y-intercept, at the a value, whatever that might be, and then it's going to start to slow its increase down, and it's going to flatten out, and just like it did over here in the beginning, it's going to almost look like it actually collides with that x-axis, but that's because it gets so extremely close that we can't actually see the difference between the x-axis and the value on our graph. Okay, so if you're looking at a graph, look for these common themes. Look for something that seems like it's sitting on a floor at some point, and look for something that has a curve to it, because it's not going to have a constant growth. It's either going to grow slowly and then pick up the pace, or it's going to decrease quickly and then slow itself down. All right, and the last thing I want to talk about today is if your function is presented to you in a table format. How do you know if you're looking at an exponential function? And if you remember back to when we talked about linear functions, we looked for a very specific pattern in the outputs. If you were dealing with a linear function, you saw a constant addition or constant subtraction in between your y values. And if you remember, I always said be careful with that word pattern, because we are going to see different kinds of patterns. So when I'm looking at this table here, the first thing I check is on the x column. I'm going up by one x value every single time. So that means I have a constant increase in my independent variables, which is going to reassure me that I don't really have to do much work here. It's always going to increase by +1. My focus then comes to the outputs. What's actually happening to these x values when I plug them into my function? All right, well, I go from 1/2, and then with one more x value, I go to 1. I can either get there by adding 1/2 to 1/2, which makes 1, or doubling 1/2, which makes 1. And the only pattern that remains true, if you look at the next step, I can't add 1/2 to 1 and get 2, but I can double 1 and get 2, and double 2 and get 4, and double 4 and get 8. So the pattern here is actually using a common ratio, we call it, which means that there is a constant multiplier. Okay, so this 2 is our common ratio. And the fact that we're multiplying by 2 every single time tells me that I have an exponential function. Okay, let's look at another one. X, Y. Oh, I think that's far enough. 1, 2, 6, 3, 15, 75, 375, 1875, and I gotta do this calculation real quick. Okay. All right, so I'll give you a hint. You are dealing with an exponential function. The separation between these two might not be too big, but then when you get down here, you've got a pretty large gap in between them. Okay, can you find the common ratio between these? What am I multiplying by every single time as I move from one y value to the next? Okay. In this case, multiply by 5, multiply by 5, multiply by 5. Ms. Bernatsky, how do you know that? Okay, well, I made the problem, so that's pretty easy. But let's say I look at any of these pairs, any of these rows, I can ask myself, how do I get from 3 to 15? I can ask myself, how do I also get from 15 to 75? Or I can just take two of them and divide backwards. Okay, what is 9,375 divided by 1875? And that's 5. And the beautiful thing about an exponential function, if it truly is an exponential function, is that'll be the same number you get if you divide this by this, or this by this, or this by this, or this by this, or this by this. That's why we call it a common ratio. All right, the last one that I want you to look at down here is a curveball for some people, can throw some people off. But the question is, what is my common ratio? First, I should be asking, is this exponential? But I'll give it away. Yes, it is. Okay, I've got a constant change of +1 in my x's, but I don't have a constant change of addition or subtraction in my y's. So I don't have a linear function. My next check is, do I have an exponential function? If I can't find a pattern of addition or subtraction, can I find a pattern of multiplication? And it's important to recognize that it's always a pattern of multiplication. Some people might be looking at the screen right away and they know that you're dividing by a certain number every time. But I can't use that number that I'm dividing by. You have to kind of flip the script on yourself and think, okay, if I'm dividing by the same number every time, what am I multiplying by? Okay, for example, if you looked at this and said, whoo, dividing by 2, got it, done. Your common ratio is not 2, because the common ratio is what are you multiplying by every single time. So remember, dividing by 2 is the same as multiplying by 1/2. This would be multiplying by 1/2, and so would this one. Okay, and if that doesn't jump out to you, remember you can actually find the common ratio by dividing backwards. Okay, look over here at the end of the table. If I take 7.5 and divide that by the y value that comes right before it, 7.5 divided by 15 is equal to 0.5, aka 1/2. So my exponential equation for any of these tables would have this number 0.5 in the parentheses that's being raised to the x power, or this 5 or this 2, because those are the common ratios. Okay? Let me know if you have any questions, guys, and we'll continue practicing this tomorrow. Have a great day.